A quick question that your grade 1 teacher probably asked you. What's 1 plus 2? Katie, what's 1 plus 2? Look at that. I asked Katie that question because I knew she would nail that question. Perfect, Katie. It is 3. Yes. Well, at least that's what you learn in grade 1. When you're adding scalars together, your grade 1 teacher taught you how to add scalars together, although he or she probably never told you that. But that's in essence what they were doing, teaching you how to add scalars together. 1 plus 2 is equal to 3. Somewhere down the road, maybe grade 6, maybe grade 7, you were taught to add vectors together, although they probably weren't called vectors, or at least your teacher didn't call them vectors. 1 plus 2 sometimes was 3, sometimes 1 plus 2 was -1, sometimes it was -3, and sometimes it was +1. It could have been all kinds of different things. Why? Because 1 could have been in one direction, 2 could have been in the same direction, or 1 could have been in one direction and 2 could have been in the opposite direction. In grade 1, there was no such thing as direction. 1 and 2 always made 3. In grade 7, 1 and 2 sometimes made 3, sometimes made 1, sometimes made -3, sometimes made -1, depending upon the direction that 1 and 2 were acting in. Make sense? We know how to do that, though, right? In essence, that's just adding together positive and negative numbers. Grade 9, I think it was, you learned to add vectors that were in 2 dimensions. And what do we mean by that? Well, let's say the 1 is to the right, and the 2 isn't to the right or to the left, but rather the 2 is upwards. Now we've got a vector that's this way, we've got a vector that's this way. How do we add those up? Well, it's not just as simple as saying 1 plus 2 is equal to 3, or 1 plus -2 is equal to -1. Now, when we're adding vectors together in 2 dimensions, we have to follow these rules of vector addition in 2 dimensions, which you've learned before in grade 9 math class. You just wouldn't have called it vector addition in grade 9 math class. So here's what we do. Here's what we've ultimately got to do in every single one of these problems where we're adding these vectors together in more than one dimension. We got to get a right angle triangle, right? What's a right angle? What's a triangle? It's 3 sides to it, right? It's a shape with 3 sides. What's a right angle? 90 degrees. So we need to get a triangle that has a 90-degree angle in that triangle. Then we're going to use a little bit of trigonometry. So here's how we arrive at that goal of finding this right-angled triangle so that we can use trigonometry. The first thing we got to do is draw a vector diagram. And the vector diagram has certain rules. The first rule is you got to draw a vector. The vector is a line segment with an arrow showing direction. So we got a vector that was, let's say it was 1 to the right. And we drew it as a line segment. We had an arrow on the end of it pointing to the right. If we had 2 upwards, then we had a line segment with an arrow pointing upwards. Notice the line segment that's 2 is about twice as long as the one that's 1. We should also draw these vectors to scale as much as possible, at least. So we need to physically take out a ruler, but draw it as much as possible to scale. Oh, now we got to put these vectors together. We have to draw them front to back. This is the front of a vector. This is the back of a vector. This is the front of the other vector. This is the back of the other vector. These 2 vectors have to be touching each other, but they have to be touching each other such that the front of one vector is touching the back of the next vector. So it could look like this. We have our first vector. There's the front of the first vector. There's the back of the second vector. It could also go like this. Here's the second vector. The front of the second vector goes to the back of the first vector. Either one of those would be okay because either one of those follows that rule that says vectors should be drawn front to back. Now, we haven't added anything together yet. The rules of vector addition require us to get a right-angled triangle so that we can use some trigonometry and such. We've just drawn a couple of vectors. We still don't even have a triangle, let alone a right-angled triangle. What are we going to do at this point to finally add these vectors together? We have to draw another line that is the sum of the vectors. If I said, what's the sum of 1 plus 2? You'd usually say 3. But in grade 7, you learned it was sometimes negative 1, the sum of 1 plus 2. Now, you learn that the sum of 1 plus 2 is the hypotenuse of this triangle. Notice this hypotenuse, or this resultant vector, we call it, is drawn not from front to back, but it's drawn back to back and front to front. So it doesn't follow the second rule. The two vectors that we're adding together have to follow that second rule, but the sum of the vectors, the resultant vector, goes exactly opposite to that rule. It's drawn back to back and front to front. In other words, it's drawn from start to finish. What if I had drawn my vector diagram like this? Because I could have, that's legitimate. Then my resultant would look like this. In other words, take a look at those red vectors. 1 plus 2 is equal to whatever that red vector is. 2 plus 1 is equal to whatever that red vector is. Do those two red vectors look the same? Yeah, they do, Stephen, right? They do. Well, that's because they are the same, right? When you're adding vectors together, it doesn't matter what order you add them together in, any more than it matters what order you add scalars together in. Hey, Katie, you said 1 plus 2 is equal to 3. What's 2 plus 1? 3. Doesn't matter what order we add scalars. It doesn't matter what order we add vectors. Right? 1 plus 2 is equal to this. 2 plus 1 is equal to this. And this is the same as this. Now, how are we going to find the value of that red vector? We know that we've got to draw two vectors. Both vectors are line segments with arrows on the end of them showing direction. We know we've got to put those two vectors together such that the front of one vector, it goes to the back of the next vector. And we know we have to draw a resultant vector, the sum of the vectors, from start to finish, or back to back, front to front. So how do we find out what the value of that vector is? How do we find out what the sum of that vector is? Yep, notice? Close, close. SOHCAHTOA involves trigonometry, certainly involves an angle. We don't have an angle here. No, not quite. You're close though. You're dancing on here. Jessica? We're going to do the Pythagorean theorem here. So we're going to say, you guys remember the Pythagorean theorem? A squared plus B squared equals C squared? C will be our hypotenuse, right? So C will be our resultant vector. Let's call C R. R squared is equal to A squared plus B squared. Or R is equal to the square root of A squared plus B squared. In other words, in this case, R will be equal to the square root of 1 squared plus 2 squared. That's the square root of 5. And the square root of 5 is somewhere in the range of 2.2. Done, right? Well, not quite. When you added scalars together in grade 1, 1 plus 2 is equal to 3. When you added vectors together in grade 7, 1 plus 2 was equal to negative 3. 1 second here. We're not quite finished here yet, guys. In grade 7, 1 plus 2 was sometimes equal to negative 1. In other words, direction mattered not only for the numbers you were adding together, direction mattered for the answer as well. Direction matters for the answer here. Where are we going to get the direction from? We know the value, the magnitude of the sum of these vectors is 2.2. 1 plus 2 is 2.2 when they're at right angles to each other. But how do you get the direction of that 2.2? I'm going to ask Fotis because I know he knows the answer to this question. Yeah. Okay, think about why I'm asking you that question. Think about why I say you know the answer to that question. Yes, keep going. Yes, you would. You would use SOHCAHTOA. In fact, specifically, you'd use TOA. Because you've got, in all these questions, you're going to have the opposite and adjacent side. You guys know what TOA is? Tan is equal to opposite over adjacent. tan theta is equal to opposite over adjacent. That's going to be, for solving for this angle right there, and we always want to find the angle at the beginning, then we're going to say tan theta is equal to opposite over adjacent, or theta is equal to the inverse tan of opposite over adjacent here. Let's do that on our calculators to make sure you guys can get that. We're going to say second function tan, follow along with me on this one, second function tan 2 divided by 1 gives me a value of 63 degrees. Now, quick question though, what if I had found theta up here? I could do that, right? Theta is always measured at the beginning of the vector diagram. Let's find theta up there. Here we're going to say theta is equal to the inverse tan of opposite over adjacent again, but opposite is 1 over 2. I'm going to do a lightning fast calculation in my head on that one. I'm going to say it's 37 degrees. How did I know it was 37 degrees? Without actually doing a serious calculation there. I'm sorry? Yeah, 27, I mean. How did I know it was 27 degrees? How did I do that lightning fast 27 degree calculation in my head? Really, I just did a subtraction, right? What was it? Or just 90 minus 63. Yeah, just 90 minus 63. In the end, if this is 63, this one's 63, this one is always going to be, we call it the complement to that. So 90 minus 63. Now, both of those are correct. 2.2 at 63, 2.2 at 27. It's just two different ways of expressing the same thing, right? It's kind of like saying, my position right now is 2 meters to the south of Elena, okay? My position now is 1 meter to the north of Elena. Sorry, that's a bad example. 2 meters to the south of Elena right now, okay? I'm 3 meters to the south of the wall. They both express the exact same thing, right? They sound completely different, but they both express the exact same position. Okay? Those two angles, 27 degrees, 63 degrees, both express the exact same thing. It's just our reference point. Remember we talked about frame of reference is important with vectors? Okay. It's just our frame of reference is different. Okay, my frame of reference was Elena, then it was the wall. My frame of reference in the first case here is the x-axis. In the second case, it's the y-axis. All right? Let's do some examples here. I want to add two vectors together 4 times. 10 meters north and 20 meters north. You know what? We don't need to draw a vector diagram for this, do we? How come? Why not? Same direction. 10 meters north, 20 meters north. That's a grade 7 problem, right? Grade 7 vector addition problem. It's 10 plus 20 is equal to 30. And of course, it's important to say to the north. 10 meters north, 20 meters south. Again, that's a grade 7 vector problem. 10 meters north plus 20 meters south, we're going to make north positive, south negative, gives me negative 10 meters. You could express it that way, or you could say it is 10 meters to the south. "10 meters to the north, 20 meters to the east." Well, now we're dealing with 2 dimensions, right? This is what you couldn't do in grade 7. 10 meters to the north, 20 meters to the east. Is that drawn correctly? What's wrong with it? No. The sum of the vectors should be the hypotenuse. Okay, when I'm adding vectors together, the sum of them, what would be 30 meters if I was adding scalars, that's going to be the hypotenuse. So looks like I got a hypotenuse here that looks well, right? These two vectors should be drawn front to back, are they? Yeah, they are. Resultant vector, the sum of the vectors should be drawn back to back, front to front. It is. That works, that works. Is there any other way I could have drawn it? 1 plus 2 is 3. 2 plus 1 is 3, right? So I could have just as easily drawn it like this. 20 meters and then 10 meters. and I would have got a resultant vector that looks like this. In both cases, that resultant vector is going to be the square root of 20 squared plus 10 squared. The square root of 500. Gives us 23 meters. Now, it is important here to express the angle. Here is our angle for the first one. Here's our angle for the second one. The angle for the first one is going to be found by the inverse tan, the second function tan of 20 over 10. And the one over here is going to be found by the inverse tan of opposite over adjacent, or 10 over 20. All right, this half of the room, you guys are responsible for getting the first one, inverse tan of 20 over 10. You guys over here are responsible for the second one, the inverse tan of 10 over 20. This should be 22, right? Not 23. 2 degrees? Blue side gets 42 degrees. Oh, wait a second. Big fight breaking out over here on the blue side. 63 degrees. Goodness. How many people say 63 degrees? We're going to go with 63. We'll double check that in a minute. On this side, what are you going to get? Yeah, 27 degrees. Not a surprise, right? Because 90 minus 63 is going to be equal to 27 degrees. All right, so what's the sum of these vectors? It's 22 meters at 63 degrees, or you could say it's 22 meters at 27 degrees. Technically, we should express what that's relative to. In other words, we should say 63 degrees from something, 27 degrees from something, but we'll spend some time on that starting next week after our test. All right?